Hi, good morning. This is Dr. Smith, and we're going to be running over the very basic time series analysis that we looked at in class. Um, excuse me. This particular in-class assignment, very, very basic as far as it comes to time series. Like I said in class, you can spend an entire semester or more only looking at time series analysis. It can get very complex. There's a lot of subtleties and things that you need to look at in it. But for our purposes, this is just a very brief introduction of how to use time in a regression, in a very basic regression analysis. So what we have here is a scenario where we are regressing the fertility rate, that's our dependent variable, on a couple variables that might impact the general fertility rate. Some of those variables are the personal exemption in the U.S. tax code, the idea being if the government gives you more money off your taxes every year, then you might be willing to have more children. I don't know. We'll be able to test that. Other things, there's a dummy variable for after birth control or after the pill became available. So dummy variable for the years during World War II. And then we have a linear and a quadratic time trend variable that's measured in years. So we run that regression and we get this analysis this is given in the in-class assignment. And we basically have this output from Excel. We have an intercept of 124. Remember, our dependent variable in this case is the general fertility rate, which means the way that we interpret these coefficients is always in terms of the units of the general fertility rate, which is births per 1,000 women. Okay, so that's basically all of these coefficients here. The way you always interpret a coefficient is in the units of the dependent variable. So since our dependent variable is the children born per 1,000 women, then we come down here, all of these numbers are the births per 1,000 women. Okay, so that's, we will say that phrase, births per 1,000 women, a lot of times, because that is the unit of all of these coefficients. We have some standard errors, some t-statistics, which we'll get to in a minute, and the p-values, which we'll use to do some hypothesis testing. So let's go ahead and jump into number one. Explain the effect of increasing the personal exemption by $1. Is this result significant at the 1% level? So anytime we're talking about explaining the effect or explaining the relationship or the slope, anything like that, we're looking at the coefficients, right? Those coefficients are the relationship. They are the effect of these independent variables on their dependent variable, which is the general fertility rate. So if we want to know what is the effect of increasing the personal exemption by $1, remember these coefficients are the effect of a 1 unit increase in x. And in this case, if our x is personal exemption, a 1 unit increase in personal exemption is a $1 increase. And so we can just come here and look at the coefficient on our personal exemption variable. And this tells us that the effect of increasing the personal exemption by $1, holding everything else equal, would be to increase the general fertility rate by 0.3478 births per 1,000 women. All right, so let me go ahead and write that in here. So what is the effect? Let's see, increasing the personal exemption by $1, holding all else equal, would increase the general fertility rate by 0.3478 births per, let's write this up, per 1,000 women. Okay. Now, is this result significant at the 1% level? Anytime you see that word significant, you should think, oh, I need to know the p-value, because what we're doing is we're testing a hypothesis. To test a hypothesis, you need a p-value. Since we're testing a hypothesis about the personal exemption, we need to look at the p-value of the personal exemption variable, which is right here. Now, this p-value is very, very small. that E negative 12 means 10 to the negative 12th power. So what this is meaning is essentially there are 12 zeros in front of the 191. So 0.0000, a whole bunch more zeros, 191. So very, very, very small p-value in this case. So if we're testing at the 1% level, we have to come here and say, okay, is our p-value less than 1%? If it is, we'll reject the null and say that it is a significant variable. In this case, our p-value is definitely less than 1%. Remember, 1% is 0.01. This is 0.000000, I don't know how many zeros I just said, 191. So this is much smaller than 1%. So what we can say then is, since the p-value, if I can type, p-value of personal exemption is less than 1%, we reject the null and the variable is significant. All right, there we go. Great. Number 2, how did the discovery of the birth control pill affect fertility in the U.S.? So we come up here, and so what this birth control, what this pill variable is it is a dummy variable that's essentially one after the discovery of the birth control pill. So basically in years, I think it's past either late 1940s, early 1950s. I have to go back and look at the data to know exactly. And so after those years, we have this birth control pill that's the variable's taking on the value of a 1. And so what this is telling us, again, we come up here and look at our coefficient. This says in the years when the birth control pill was available, the fertility rate was 10 lower than the years that it was not available. Okay, so come here and write that down here. So in the years when the pill was available, all else equal, the fertility rate was about 10 births per 1,000 women less than before it was available. What about in World War II? So World War II is a dummy variable that was held a 1 during the years of World War II. And so what this is saying is during World War II, the fertility rate was, we'll say, almost 36 births per 1,000 women less than in other years. Okay? Are these significant at the 5% level? So let's start with the pill. We come here and we look at the pill. Again, testing significance, we always look at the p-value. So we come look at the pill's p-value. Oh, the pill's p-value is 11%, which means the p-value is higher than 5%, which means it is not significant. Okay? But the World War II p-value, again, very small. And that is less than 5%, so the World War II difference is significant. So we'll go ahead and type that here. The pill variable is not significant since its p-value is greater than 5%. But the World War II variable is, since its p-value is less than 5%. All right. So, all right, number 3. seeing a graph of fertility rate by year. So this is an actual graph of the data by year. Why do you think we include the quadratic trend variable? Could someone make a case for even including a cubic time trend? Why or why not? So let's start off with why do we just include the quadratic? So including a quadratic variable, again, if you think that the relationship that another year has on the fertility rate depends on what year we're in, then you need to include some other, higher order variables. So we've been using quadratic variables. Now, looking at the graph of it gives you kind of a pretty good idea of what kind of variable that you would want to include, because if we included a linear, so let me show you the difference between linear, quadratic, and cubic. So I kind of drew these out earlier today. A linear trend is just a line, right? That's why it's called linear. So if we came over here and in this graph drew a line through this, I mean, that would be okay, but it wouldn't do a fantastic job of explaining the relationship between time and the fertility rate, right? I mean, there's obviously something going on here that's not just a linear relationship. We see it going down in some years and then up and then back down again. And then it's kind of leveling off at the end. So a pure linear trend might not be the best thing. Now, if we did a quadratic trend, what that allows us to do is fit basically a hill or a U shape to this. Now, again, in this particular case, that does okay, right? Because we see over here we have a U shape, right here we have a U shape, but that's not going to be great, okay? That's not going to be perfect. It might be better than linear, but it's not going to be great because it's not just a U-shaped graph here. It's like there's almost kind of two humps, right? There's one going down and one going up. So we have both kind of a minimum here and a maximum. That's different than just a parabola where you would have just say a maximum or a minimum. So if we look at a cubic function, which I have a picture of over here, a cubic function, very much like we just saw, has two humps, always one going down, one going up, right? And so in this case, we have this one minimum and one maximum, and so we get this shape that's very, very similar to what we're actually seeing here. So a cubic time trend would make a lot more sense to include here than even a linear and a quadratic. Now, in class, I haven't showed you how to do cubic variables yet, and you have to use some calculus to figure out the actual relationship, and so we didn't get into that. But just what I wanted you to see is that even a quadratic shape here doesn't do this graph justice. You would really need a cubic trend to really match this pattern, okay? Now, am I going to ask something like this on the test? Probably not, okay? But I wanted you to kind of understand the difference between cubic and quadratic. So let's just answer the question here. Why do we include the quadratic time trend variable? There's obviously more going on in this graph than a pure linear relationship. And so including higher order variables like quadratic, it's spelled quadratic, might capture change, or might capture the relationship. Could someone make a case for even including a cubic time trend? A cubic trend variable would absolutely make sense here, because the graph seems to display a cubic function. And there we go. That's fine. Am I going to ask that on the test? No. But I did want you to kind of see it in class so that we can kind of discuss it. All right. Number 4. Write out a formula that allows us to calculate the change in the fertility rate due to an increase in the year. So if we come up here, we look at the year. Up here, we have a t and a t squared. Remember, t is our time trend. And so anytime you have that squared variable, we're going to have to use our quadratic slope formula. So remember, our quadratic slope formula is, slope is equal to beta linear plus 2 beta quad x. Oops. 2 beta quad x. All right. So in this case, our beta linear is the coefficient on the linear variable, which is the one that's not squared. So negative, we'll say 2.5314. So that's negative 2.5314 plus 2 times, and what's beta quad? Beta quad is the coefficient on our squared variable, so 0.0196. So 0.0196 times x, and in this case, our x, the variable that we care about is t. Okay? So that is our equation, and now we're going to use that equation here in number 5. How does moving from 1913, which is the first year, t equals 1, to 1914 affect the fertility rate? So what we're going to do is we're going to plug into our equation here t equals 1. So the slope is equal to negative 2.5314 plus 2 times 0.0196 times 1. And then I'm going to take my calculator here. And let's plug that in. So we'll go ahead and do the first part. So 2 times 0.0196, and we'll do the 2.5314, and we get negative 2.4922. So negative 2.4922. So in the first year, we expect the fertility rate to fall by about 2.5 births per 1,000 women. Okay, so now let's move to the next question, which is, what about at t equals 70? So we'll come here and we will do slope. Spell slope correctly. Negative 2.5314 plus 2 times 0.0196 times 70. Okay, and that's going to be equal to, let's come over here and do that. So 2 times 0.0196 times 70 is 2.74 minus 2.5314. We get 0.2126. Okay, awesome. Now, last question. At what value of t is there no effect on the fertility rate? No effect means the slope is equal to 0. And so what we can do then is come here and find out at what point is the slope equal to 0. So the way we're going to solve that is we're going to solve for t when the slope is 0. So let's do that. So we'll say our slope is 0 equals negative 2.5314 plus 2 times 0.0196 times t. We're going to solve for t here. Okay. After some algebra, what you'll find out is that t will be equal to 2.5314 divided by 2 times 0.0196. All right, and then that is equal to, say, 2.5314. 64 point, we'll say 5765. Okay, now is what year is that? So when t equals 1, that is 1913. So when t is equal to 64, right, t would equal to 64 in 1976. So go up here. I'll do this afterwards. That's 1976, since t equals 1 in 1913. All right. That's it. That's all there is to it. And we will go over this in class on our review day. And if you have any questions, you can always feel free to email me. Thanks, guys.